Hi everyone, my name is Mayor Andalibi and I'm a fourth year electrical engineering student at Lassonde School of Engineering. I'm also one of the students in the course EECS4641, which is the Introduction to Medical Devices and Biological Instruments. EECS4641 allows students to gain knowledge about how to use op-amps to design low-pass, high-pass, or bandpass filters. The course starts with the basics of op-amps and their application, and then you learn about the analysis of complex multi-stage op-amps. And finally, you learn about the design and how to achieve the type of filter you want using op-amps. I personally learned a lot in this course since my knowledge about op-amps was very limited before taking the course, but right now I can design different circuitry using op-amps to achieve the type of filter I want.
Hey, my name is Rishabh Bhatnagar. I'm a fourth year electrical engineer. I would highly recommend taking ECS 4641 because it allows you to learn about electrical engineering from a very different perspective, specifically a biological one. It allows you to learn how different biological devices work and function, and how to design and build them for these specific applications.
Hi, my name is Richard Tilkov. I'm an electrical engineering student at York University, the Lassonde School of Engineering. ECS 4641 is an interesting course because we get to take our electrical engineering concepts that we've learned so far and apply them to the biomedical field. We learn how to design different devices, filters, and amplifiers to measure biomedical signals.
Welcome to the explanation portion of this video. Our goal was to measure different neck movements using electromyography, such as looking left or right or different irregular neck movements. What do we expect? Well, we expect the neck to always be under some level of stress as it has to hold up the head. We expect both sides of the neck to have roughly the same strength, and we expect that when you either look left or right, for example, that one muscle will be activated and the other one will be deactivated or will be less stressed. As you can see, both sides of the neck have their own respective muscle, and then hence electrodes are placed there. And as can be seen, the BioPack software was used in order to capture the electromyography signal and export it into MATLAB. As can be seen, however, there's a lot of noise. This could be due to electrode placement or many other things, and this needs to be corrected through different signal processing techniques, as can be seen listed here. So the first one is the same as what was done in the first lab, which is taking the floating point, taking the moving average, and applying that to the signal. This now goes to taking a low-pass filter. So as you can see, since there's a low-pass filter, a lot of the high-frequency noise has been canceled out. Removing the DC component is the same as taking the signal from an offset and removing it. This can be used, for example, for the nodding signal, where we can see the users either activating the muscle or deactivating the muscle, hence nodding. Hence it's also very periodic. Observing how the signal changes over time is taking the derivative of the function, which is the rate of change, and we can see how much the signal changes. Taking the absolute value and the mean tells us is a measure of how much the signal is changing over time or how much activity there is over time. As can be seen here, when the muscle is not stressed, the derivative is relatively flat. When the muscle is being used, however, there's a lot of change, hence the noise that's there. Observing different elements, so we use a wavelet transform in order to get the energy spectral density of the function. This was then used in order to see how periodic the function was using autocorrelation, and this was used for the rolling gesture. As can be seen here, we take the wavelet transform and we get the wavelet outputs of the third and fourth coefficients, and we use the autocorrelation to see if the gesture is periodic or not. Again, this was used for the rolling. So for example, if you use the rolling data, we wrote MATLAB code to decipher this into the specific gesture. So for this case, you double click rolling, you run the code, it will run a bunch of mathematical calculations, and through its best estimate, it'll say, for example, that you're rolling.
In this part, I will be explaining the explanation from the previous section. So first, we're going to load up the looking to the left data. And then now running the algorithm, and then looking at the graph. The first graph is the correlation between channel 1 and channel 2. As we can see, the two graphs, the correlation is correct because from the two graphs are symmetrical at 0 and the maximum amplitude is happening at 0. Next one is the wavelet function. These two graphs, the two left ones, are the third wavelets, and then the two on the right are the fourth wavelets. This is the data after applying the low-pass filter to it. The difference between figure 2 and figure 3 is that they're basically the same data, but then figure 3 actually has the average mean of the last 50 points, which means basically similar to applying a low-pass filter. And then the first graph is basically the data without applying any, which is the raw data without applying anything to it. And as we can see from the output right here, it says that you're looking to the left. So let's just say if I right now click on looking to the right, loading up the right data. Now I click on the run section, and it says you're looking to the right, and the graphs are different. So the correlation for looking to the right is different from correlation to looking to the left. Same with the third and the fourth wavelets. Same with the data and the way that they work. We apply it to the rolling. We can see that it says, I think you're rolling your head. Now we can see at 0, the peak amplitudes are a lot more. And then the third and fourth wavelets are different. As you can see, the channel 2, we can see there's a wavelet and there's no tension right here, and there's tension right here in the muscles. Same with right here. So now we can see a more periodic movement of the graphs. Same with right here. When we apply the last 50, the mean of the last 50 points. Now if we just look at the yes motion, the last one. So it says, I think you're nodding yes, the correlation, the third wavelets and fourth wavelets, and then the low pass the data with the low pass filter, the differentiation of the two channels, and then the actual graphs.
What are the uses? What are the applications of a project? Well, the neck is a very important part of the human body as it holds up the head, and the health of the neck is very, very important, and it can cause a great deal of pain if it sprains. So detecting movements such as whether or not if someone is looking too far left or right or moving the neck irregularly for long periods of time is very important for the health of the neck. As for incorporating this into different technologies, EMG, which is what we used, is an industry-wide used piece of technology. So it can be integrated in things such as scarves or bands you can wear. And this can be used and combined with the fact that the program written for this project is a simple mathematical program. Combining everything together, this can be all simplified. This whole project can be simplified into nothing but a small microcontroller and a few electrodes.
I would recommend EECS4641 to other students, as I was able to learn a lot, especially when we were working on the project, as I was able to apply the knowledge from the lecture material to a real-life application.
What I found most interesting about this project is how we can take a signal of the body doing some kind of gesture and break that down into data that can be classified and differentiated between other gestures, and learning how to most effectively do this process.